So next up, the case of the misaligned shaft. Alright, we got this shaft here, 2-inch diameter. It's mounted with 3 bearings on it. Problem is one of these bearings is mounted half an inch too low compared to the others. So material properties, Young's modulus is 29 times 10 to the 6 psi. It's a steel. We've got our I here. Well, not a material property, it's a geometric property, but anyways, plugging in the 2 inches there works out to 2.7854 inches to the fourth. And our area is pi inches squared. So we get the maximum, we want to find the maximum bending stress, and we want to find out what the reactions are. So I just redrew this free body diagram here. Got our reactions that we can look for. So Cx is simple to find. It's 0 because it's the only one. So we want to kind of look at what situation matches this. So it's relatively simple. It is a point load in the middle of a simply supported shaft. So we're looking at Patel case number 1 here. So we can find the formula for kind of how it varies from A to P here, or we're not really too worried about that, what's happening in the middle there. We just really need to know what's happening at the maximum. We know that it's the middle part that is mounted too low, so we can find out we know how low it's mounted, so we can find out what sort of reaction force is caused by that. So I have that formula there. So yeah, the displacement in the centers equal to P times L cubed divided by 48 EI. So our displacement's minus 0.5 inches, and our L and our BY is a negative as well, our load's a negative as well. So negative BY. L is 96 inches, so that cubed divided by 45 times R, 29 times 10 to the 6 pounds per inch squared, and our I is 0.7854 inches to the fourth. So we end up getting this value here. Our units, so when we cancel out, we got the pounds on the bottom. We got pounds to the fourth, sorry, inches to the fourth, divide on the bottom, but and divided out by another inches to the inches squared. So on those two combined, it gives us inches squared on the bottom. And we get inches to cubed on the top, so it ends up just being inches on the top. Inch, so the units there is inches per pound. So solving for BY, just take our 0.5 inches, divide by that. So 0.5 inches divided by 8.093 times 10 to the 4 inches per pound. The inches cancel out, and the pound moves to the top, so that gives us a BY of 617.9 pounds force. And while we're looking at this thing, it's symmetrical, so we can just say that AY is going to be equal to CY, and the magnitude of that's going to be half of this. So our reactions are going to be 308.9 pounds. So our shear diagram is fairly simple. I got the first reaction here that bumps us up down here. That bumps us up to 308.9. That stays constant until we hit the the misaligned bearing, and then it pulls us downwards, and it pulls us downwards to minus 308.9 pounds. And that continues all the way until we hit the other end, and then we hit the reaction here, which brings us back up to 0. So our moment, so the magnitude, so the moment starts at 0 on each end, and it grows. It's a linear relationship. The slope of that line is equal to the magnitude of the shear there. So the maximum shear that we're going to reach is 308.9 pounds times 48 inches, so 14,872 pound inches. Sorry, my alarm just went off there. So yeah, that is that's our magnitude of that's our bending moment there. So we can figure out what our bending stresses are. So again, our bending stresses is going to be negative our moment times our y position divided by I. So again, we've got another circular cross section here. So the maximum I and the minimum I are the same magnitude. So I'm going to say, here that our bending stress, our maximum bending stress, is plus or minus the 14,823 pound inches times the 1 inch plus or minus 1 inch divided by our 0.7854 inches to the fourth. So again, inches, those 2 inches cancel out this 2 inches squared, and multiplying everything out gives us 18.9 KSI. So again, it will be compression on the top, tension on the bottom. When our y value is positive here, because we have a positive moment, the bending stress is negative, and we have a negative y here, so negative 1 inch down here. Then we have a positive tensile stress at the bottom.